Meta-learning, or learning to learn, enables models to adapt quickly to new tasks. But one limitation is that we don't know whether the model truly understands the underlying task features. Our method, Disentangled Multi-Context Meta-Learning, DMCM, learns multiple context vectors, each corresponding to a distinct factor of variation. For example, in sine regression, amplitude and phase shift are disentangled into separate contexts, understanding the feature difference. With our model, each task's context is disentangled into meaningful components. Because these contexts explicitly represent the corresponding task feature, they can be reused and shared. For example, we can take the amplitude context from one task and the phase shift context from another and combine them to predict a new sine function that shares those properties. This enables powerful zero-shot generalization to tasks that share known contexts. Various applications are enabled by this concept. For example, we can intentionally extract certain dynamics factor from short real-world data and recombine them with easily available simulation data. Then, we can create diverse dynamics scenarios containing real-world factors. This idea is extended to quadrupedal robot locomotion task. DMCM disentangles terrain characteristics and robot-specific properties in robot dynamics model. By recombining these, the model shows high-performance stair climbing in the real world using only 20 seconds of real data at flat terrain without real-world stair data. Task generalization is not the only merit of our model. DMCM shows robust performance in out-of-distribution tasks through deep understanding about task features. At sine task, DMCM shows similar performance with various baseline models with full training range. However, DMCM shows robust performance at out-of-distribution training range at both 2 context and 3 context cases. This robustness is also shown at quadrupedal robot locomotion policy. To train and compare locomotion policies, we first build robot dynamics models with 2 approaches: DMCM, our method that disentangles terrain features, and robot-specific features, and Cavia, a standard meta-learning model that encodes features into a single entangled context. We compared 3 policies. Multi-DMCM policy, who can use disentangled terrain and robot property context vector from DMCM dynamics model for context information. Vanilla policy, which serves as a baseline without any context information. Single Cavia policy, which uses a single entangled task context from Cavia dynamics model. We can recombine the disentangled context from different datasets at multi-DMCM model, while single Cavia model cannot. In real-world deployment, all 3 policies succeed on in-distribution tasks, climbing a 17-centimeter stair with LiDAR payload. However, the single Cavia model takes longer, since its entangled representation prevents it from effectively using real-world data from flat terrain. At out-of-distribution task, where KP gain of motors are set quite low, multi-DMCM model and vanilla policy could climb stairs, while multi-DMCM policies showed higher success rate and shorter success time. However, single Cavia policy failed the task with both simulation stair data and real-world flat terrain data. Multi-DMCM also proves robust performance with asymmetric payloads like water bottles on 3 legs. The policy successfully moves on both wavy and stair terrains, utilizing disentangled contexts. Thanks to its robustness and generalization capabilities, our DMCM framework holds strong potential for broader applications in robotics. Thanks for watching.